All right, well, hello, y'all. Sorry about the last few days. What I'm going to do is do the first part of day two and hopefully get this posted really soon so you all can get up and working. This is going to be a more practice with writing programs. And the program I want to do with you all right now is adding vectors. Write a program that'll add two-dimensional vectors. Um, Whenever I do a recording, I really encourage students to pause at some point and see if they can figure things out for themselves. So this recording is going to be a lot less than an hour and 10 minutes. If anything I go over that you feel like, hey, I got that, I remember that, I don't need a review, feel free to fast forward through or to put it on 1.5 times speed, etc. I want you to do whatever works best for you so that you can comfortably write this program and understand what to do. As far as what you need, hopefully you have MATLAB up on your computer. I think a calculator is helpful to have. I think so when you do programming with numerical stuff, a lot of times it's helpful to say, hey, can I do this quick calculation and then check to see whether my program came up with it correctly. Okay, so super quick review on vectors. We have this idea that, hey, we can start with vectors by just thinking about our simple trigonometry, geometry, etc., and thinking of vectors for lengths or displacement. So what if you had a displacement of 4 units followed by a displacement of 3 units? Oh, look, you all know that that's equivalent to a displacement of 5 units. And that, of course, makes sense. You've done that forever with geometry, that you can say like, well, look, we can add these two by drawing a rectangle, probably a triangle with 4 and 3, draw the hypotenuse, and then get the length of that hypotenuse and get this angle in here. So you all know that the length of the hypotenuse is 5. The angle, we're going to do inverse tangent, 3/4. Okay. And I don't have that one memorized, so give me just a second to do that on my calculator. Hang on for just a second, please. And when I punch that into my calculator, I get 36.9 degrees. So, I mean, not to be overly detailed about that, hey, it works, If you had someone who went 4 meters this way and then 3 meters that way, and someone else went 5 meters at 36.9 degrees, they would end up at the same spot. So we could say vectorially, we could say essentially a vector of 4 plus a vector of 3 is a vector of 5 at an angle of 36.9 degrees. Okay, that's not precise notation, but hopefully you get the point that was going on. Okay, what is kind of interesting, but maybe not that surprising. Hey, does it work for velocity? If you had a velocity of 4 meters per second and a velocity of 3 meters per second, as simultaneously, would that be equivalent to a velocity of 5 meters per second? And indeed it does. Does it work for acceleration? Yes. Does it work for force? Yes. Does it work for the strength of magnetic fields? Yes. It works for all quantities in physics, mathematics, etc., that are vectors. Okay. So what we want to do is add vectors, though, that are not necessarily orthogonal or at right angles. So how do we go about doing that? Well, the first thing we're going to want to be able to do is take components of a vector. So let's just remind ourselves super quick how to do that. And then let's try to write a script file that'll do that for us nicely. So really quickly, let me do a little bit of racing and get that up there. No need to take any notes for this. Again, if this is something you're super comfortable with, fast forward or put it on 1.5 speed. But let's imagine then that we have, this is the x-axis here like this. This is the y-axis. We're going to do our angle as rotation counterclockwise from the x-axis. So let's say we have a theta of equal to 80 degrees. Okay. And we have a force, okay, of 100 newtons. Okay. So representing what that's going on, that would be, give me just a second here. That would be a force of 100 newtons, kind of like that. That's 80 degrees there, like that. Okay, that would be equivalent, a pull of that. If you imagine this is an overhead view and you had like a sack of rice or something like that, that would be equivalent to one person pulling this way with a certain amount of force, and one person pulling another person pulling this way with a certain amount of force. So let me draw it just a little bit differently. So we found the right components, a person pulling this way and a person pulling this way. It will be equivalent to one person pulling 100 newtons of that, like that. So there's that stack there. So just a quick reminder, we're going to call this Fx, we're going to call this Fy. Eventually you get very comfortable and you don't need to draw your rectangle, but your triangle. I'll put it there like that. This is going to be the adjacent component to our axis, to our angle. So f of x is going to be the f cosine theta, and fy is going to be equal to f sine theta. Okay, and let's get the numbers up there so we can look at it really quickly. You can check my math. I know this is not live, but I love it in class when people check my math to make sure we're on the right track. Hang on for just a second. Yeah, so I get rounding off to 1 decimal place. Okay, I'll do 2 decimal places. That'll make things easy for us. We're going to do later on. So that's 13.89 newtons. Sorry, I'm fumbling a little bit. 78.78 newtons. All right. So why don't you go ahead and brainstorm? I encourage you to pause for a second and brainstorm a bit and say, look, if I want to write a script file that says to the user, input the force, its magnitude. Hang on for just a second here. I'm going to pause and fix up a couple of these numbers. I think I have a mistake. Okay, so too bad we weren't in class, so someone couldn't catch me. So 100 times cosine 80, I'm getting 17.36 newtons. Okay, and 100 times sine 80, I'm getting 98.48 newtons. Sorry about that mistake earlier. Okay, so again, I'm encouraging you to pause for a second, brainstorm a little bit. How am I going to write a script file that does that? It asks the user input your force magnitude, input your force direction, and then it's going to output the x component of that force and also the y component of that force. Hey, we'll meet up in a couple of minutes and take a look about how to do that in MATLAB. Okay, so hopefully you're seeing MATLAB on there. Take a look at what I got. I have kind of something kind of weird here that's bothering me a little bit that you don't see. Pardon me. Okay. So I'm at the command window, so I need to get a new script. By the way, you don't need to follow all of this if you got it. I got a new script. Pardon me. I'm going to call it 2D vect comp. So I'm going to save it as, hang on just a minute. So try to have a pretty short name so it's not super long. I got 2D vec comp. And hopefully that'll do it for me. Okay. Right. So right now it doesn't, I'm being a little bit particular and I'm just gonna just put something in there to make sure it works. I got kind of a weird thing going on with my right now, so I'm just gonna try to run that. Shoot, I have a problem with my naming, so hang on for just a second. Yeah, I'm back. Sorry about my voice. So I got my actually called it force comps, and I have my start right there. So Hopefully you're getting the idea that it's helpful to have a little bit of documentation. So there's my percent. I'm going to describe what they do. So there it is. And then I want to get going and try to get my inputs in there. So let me go ahead and work on that, and then we'll go ahead and take a look at how that works. Okay. By the way, it's a little bit awkward. This is my first time going through and trying to do Zoom with MATLAB. So hopefully by the end of this lecture, I'll be better at it. So I said F magnitude equals input force magnitude to get that instruction. Try to start looking over to the right as you do it, and notice that there's a yellow bar there. So there can be green, yellow, or red bars. Let's go ahead and run it and take a look at what happens. Okay, so that's looking good. Input force magnitude, say 100. Okay. And then on the command window, F magnitude equals 100 comes up. So hey, maybe when it runs, we'd like to see that, or maybe we would like the script actually not to show that. So this yellow here gives us a warning. And if you put your cursor over the yellow, it describes what the warning is. So the warning says that it's suggesting to add a semicolon so to hide the output. So I'm going to try that and run it again and see what's going on. Right? So I'm going to go ahead and run it. This is input force magnitude. I've got 100, and then it doesn't show anything else. Okay, so I'm going to pause for a second and try to get the force angle and a little bit more in there. And I encourage you to work on your own, and we'll come together again in a few minutes and see how that's all working. All right. I've done a little work, and I hope you have too. Let's take a look at what I did. So I called the angle theta, and I remember, look, if I want to figure out the x component, I'm going to have to multiply by the cosine of that angle. But when MATLAB does cosine, it wants the angle in radians. So I had to take that theta and convert it to radians, and then I did F magnitude times cosine cosine of radians. So I got my warnings over there. They're all about adding a semicolon. So I'm going to add the semicolon after this one. And then one of the warnings goes away. I'm not going to add it over on the other two. And let's just run it and see what happens. So it asks for the force magnitude, 100. And it asks for an input magnitude, and we were doing 80. That's what's on the board behind me is 80. Okay, let's see what happens. Okay, so taking a look a little bit, I'm going to move this up and taking a look what happened. It said theta equals 80. I want to eliminate that. And then it said fx is 17.36, and that's what we wanted. So we're on the right track. I'm going to go ahead and pause and finish this off and make sure it's working. And I encourage you to do it yourself so that you can take a force, input a direction, and it should pump out the right magnitude. Let's give it a try. Okay, let's take a look and see. Right. So I've got fx calculated and fy, and then I actually put a colon there, so at that point it doesn't put that out. That's not necessary. If I stopped at this point right here, it would actually put out fx and fy equals, but I wanted to get a little verbiage in there to help the user. And so I use the display command, which is one command we want to be really good at. So let's just give it a try and see if this works. We'll do it 2 times. Force underscore comps. Okay. So in the command input force magnitude 100, and our angle was 80. And it's cut off a little bit, so I'm going to adjust this here so we take a look. So to put it out, the horizontal component is 17.36, the vertical component is 95.48, and it had an end of calculations to show you the program's done. Okay, so when you do anything like that, it's good to run a few test cases. I'll just do one test case. What if the angle was 270? So I'm gonna just run it here. I can use this run command up here. Just gonna run it. Pardon me. So I'm gonna make the force magnitude 20. I'm gonna do it at an angle of 270. Before I hit return, let's think about it. That would be a downward force. So it should have no X component and its Y component should be 20. Let's just see how that turns out. Or negative 20, pardon me. So I'm checking there, I got the horizontal component is 100 and the vertical component is negative 20. Okay, so we've done what we tended to do. Let's get going and try to do the whole thing. So hang on for just a second. Actually, hey, before we go on and try to write that complete program, I'd like to come up with another way to output results or to make statements in the command window when you're doing a script file. So we have the DISP, the display command. Another important one is fprintf. And there's a lot of, that's a pretty meaty command with a lot of details. So that is in chapter 4.3.2. I think for homework number 2, you're going to have very little need to go back to the textbook. Of course, if you do, it's fine, but you probably are going to have to go back to 4.3.2 to get better at fprintf. So first of all, fprintf can be just identical to the display command, where we can just type in a string like your name or something like that, and it'll actually put that out. So let's go to the command window and see if we can do that. So there I'm at the command window. I'm going to type CLC to clear that. Okay. And I'm going to go ahead and just try to do fprintf. So a really commonly used command. I'm going to try to put like today is Saturday in there. See if that works. Quote mark. There it is. I'm out there. Okay, good enough. So that's no different than display. What's the big deal? fprintf can also put out variables. It can put out multiple lines, and it can actually also be used to do saving, etc. More about that later on. So let's go ahead and take a look at more deep an alternative for fprintf. So I believe that for the most part that you're going to use fprintf in this way. You can do a statement that looks like this. It has some verbiage in it, and it has this important part right here, starting with percent. And that is where you identify how the variable that you want to include in this statement is going to be formatted. So when you actually run this, I don't think I need to write it out. If we do it, sorry about that. Need a second. So if we do that correctly in the command window, we're going to have the force magnitude is 100 newtons. At least that's what we're supposed to do it. So some things about it. Percent indicates that we're going to have a variable that's going to be out. Okay. There's going to be a dot here. And after the dot, that's going to be the precision. So 3 digits out of the decimal point, 2 digits out of the decimal point is 7. Okay. This is going to be the formatting. And on page 106 of the textbook, it's got the different formatting options. So a common one you're going to do is if you want to go as an integer. You can use scientific notation. I did F for fixed point notation. So fixed point notation means we're going to have a number like 100 and then say like 0.00 or 0.28, etc. Okay. These other two values that you can put in there are optional. And one is going to be, we can have a plus or minus in front of it. And another is going to be the width that we can have. So I'm going to skip this one right here. When I enter it, I'm going to do percent. I'm going to try a 4. That's how wide my field is for the variable is going to be. I'm going to try to if I do a 0.2, that means I'm always going to have 2 up the decimal point and F, fixed notation. Okay, then there's the end of my verbiage, newtons. Okay, I have my quote, and that is essentially this whole script, or string that's going to come out. Then here I have the identity of the variable that I want to have come out. All right, so let's go back to MATLAB and give that a try. Okay, so I'm gonna try to do fprintf again. You don't need to do this. I'm gonna just go ahead and copy it. Fprintf, but instead I decided that I'm gonna have a string that is force magnitude. I know my typing's not correct, but I just want to take up more time. Is, okay, now I want to have my variable inserted, but I'm going to format it. So percent, that says I'm doing a variable. Okay, I'm doing it 4 wide. I've got 2 after that. And then I'm going to do fixed notation. Then I'm going to have my newtons in there, if that's what the unit system we were working in is. Okay, so now there's the statement I want to come out. I'm going to do a comma, and then I'm going to indicate the force magnitude that I want to have there. Okay, let's see. I'm going to pause for a second and take a look and see if I'm on the right track. Looks good. Let's go ahead and run it. See if we got it. Okay, it says the force magnitude is 20 newtons. Let's go ahead and change fmag. See if we can get it to work. Okay, so I changed it. So I got fmag is negative 117.333. So I'm going to try to copy that statement, fprintf, and let's see what happens. So it says the force magnitude is negative 117.33 newtons. Okay, so what I encourage you to do now, I'm going to do it myself, is try to go back to your, hang on for a second here. It's a little bit bigger. Okay, go back to your script file and replace the 4 display statements, 1, 2, 3, 4, with 2 fprintf commands. Really encourage you to give that a try. I'm going to do it myself, and then we'll come back together and see if that's working. All right, well, let's take a look at it then. So go into MATLAB. All right, so I think I did pretty well, but hopefully maybe some of you have noticed an error there. Okay, there's my force comps program or script file, and I changed it to fprintf, and then that does fx, and then I did it again, fy, and then I just wanted to have a display saying end of calculation. So let's go ahead, I'm going to go ahead and run it and see how it turns out. So I just want to go ahead and clear this, and let's move this up a little bit. So there. So 100, and then we were doing an angle of 80. So it looks pretty good, but if you focus right here, it's just doing a continual output, which is kind of confusing. So how to handle that? For reasons I don't understand, and it's not explained in a lot of MATLAB material I have, when you have multiple fprintf statements, it just keeps rolling. It rolls through all of them. So if you do the command backslash or /n at the beginning of a text or a string in fprintf, it will do a new line. So what I mean by that is I would like to do this on a new line. So I'm going to do a / and then an n. Okay. And then what that's going to do is this vertical component line should come out on a new line in the command window. So instead of having this long sentence here, a little bit hard to read, it should work out. So let's go ahead and run it and see if I got it. So force magnitude, angle. So then it puts out the force horizontal component is 17.36. The force vertical component is 9848. And it's kind of end of calculations. So I would need to do something similar to take care of that last statement. Okay, well, here's what I encourage you to do. I would maybe fool around with this a little bit more. Again, I'm a pretty results-oriented teacher. When I evaluate you, I want to see what you can do under a assessment type scenario, like a quiz or a test, and we'll use that to evaluate how your grade for the semester. I am going to include homework as a component of your semester grade. More about that later, particularly when I can talk. So, there's no way I'm going to test whether you go through and work on this a little bit to see whether you got it right. I know you have a lot to do, but I encourage you to take that pause, work on this a little bit more before we move on to the next part of this exercise. So again, the goal of this lecture was to make a script file that will add two vectors. So let's do a problem really quickly on the board. And then we're going to try to do the program and see the same results from the program. So, pardon me. So just a quick reminder, I probably won't talk very much about that, but if you have two vectors, so in this case, I've got a vector of magnitude 100 and I'm going to consider it a force vector, but it could be an acceleration, a velocity, an electric field, it could be anything. And then the second vector, F2, let's go ahead, I'm going to give it a magnitude of 50 and have it be at an angle of 135 degrees. All right, so how are you going to go about adding those two vectors? I mean, really, if you remember how to do this, I would encourage you to just go ahead and pause on the video and work it out yourself. Just a quick reminder, one way you can do is you can do the tail to head method. So you can pick up this vector here and put it at the end there and try to do a drawing on your paper. That's 100. And then I'm going to take this one right here, and it's an angle of 135. So that's back there like that. And it's a little bit shorter. That wasn't very good at 50. And my resultant vector of the addition is going to be that vector right there, from the tail of the first to the head of the second. And you can do this on graph paper. You can use a ruler, it would work. You can think about using the law of sines or law of cosines. But hopefully remember from your past work in physics and mathematics that another great technique is to get the components of F1, components of F2, and then add the X components, add the Y components, and get the results. So I'm going to do the components work first. I encourage you to go ahead and pause the video and get those yourself. See if you agree with my results. Okay, so here are my results. The F1, its X component is large, 86.6. Its Y component is 50. And then for F2, its X component is negative because it's pulling to the left, and its Y component is positive. So then how do we go about adding those up? Well, we can say that the total force in the X direction is the sum of these two. And so there's going to be a little bit of force in the X direction, and the force in the Y direction is the sum of these two. So then we actually add components. So pause for a second and I'll take a look at that. Okay, so I got that the total X force of these two forces, it should be small because this is countering that forward pull. And I got 51.24, 86.6, negative 35.36. The total Y force should be pretty big because those two are working together. So I've got 50 plus 35.36 and I have 85.36. I ended up calling them, instead of doing sum of the force in the X direction, I ended up calling it FXR because I'm thinking, okay, I want to write a MATLAB program and something notation like this would be convenient. All right, so I'm still not done. The goal is to get what this force right here is. Okay, and so basically I know that I have a total in the X direction of 51.24, a total in the Y direction of 85.36. And so I can just add those up. 85.36, I can add those up. And so I'll add them up using the Pythagorean theorem. And then in addition, I need to get this angle. So I'm going to do the work on the board. I encourage you to do that yourself. And let's see if we can come up with a good result. Okay, so hopefully you pulled out your calculator and went through the work. I did it myself. And I'm thinking a little bit about how I might do this in MATLAB. So I want to take this and square it and this and square it and do the square root, and SQRT is a built-in MATLAB function that we can use. I got 95.56, and then get the angle. I'm going to get this angle theta. I'm going to do inverse tangent of the y over the x, inverse tangent of the y over the x, 59.02. Hey, and I'm ready now to go. I've reminded myself how to do things. I'm ready to go back to MATLAB and write the script file. Maybe one thing to note, when I do this, it's going to give me an answer in radians. So I need to actually convert that to degrees to get my result. And I'd like to do things like use the fprintf command. So again, I encourage you to pause the video and go ahead and get going. And I'm going to come back on in just a second and take a look at how we're going to do this in MATLAB. Okay, so we're done with this one right here. So rid of that. So here, this is the start of it. I just started out instead of asking for the entering, just to have a little something that comes on the screen. And then I got this entering F1 and its angle. Okay. And then we have two forces. So then I go down a little bit further. Just hang on for a second, just please. And then I got my two inputs. Notice that I have the semicolons at the end, so it doesn't come up. Okay. And so now at this point in the program, you'd have the two forces entered, and I got to take those angles and convert them into radians. And then after that comes the computation section. I could have done a little bit more green notation, that would have been good. But I'm figuring out FRX and FRY. And I did it in one step. I said I did F1 cosine theta 1 plus F2 cosine theta 2 and F1 cosine theta sine theta 1 and F sine theta 2. Okay, so I'm going to go ahead and pause for just a second. And again, I'm not trying to force anything down your throat, but hopefully you've seen at least one way of doing that, and you can work for a little bit longer and see if you can make this thing work. Look for those yellow marks on the right side and those red marks on the right side. See if you can hover over it and do some fixing and see if you can get this to work. By the way, when I ask you to submit a script file for homework, even if it doesn't work, as long as you've made good progress on it, I can take it, copy it and paste it and put it into MATLAB and say, okay, they didn't get it all, but they're on the right track. That's good stuff. So right now, good stuff would be to make as much progress as you can. Okay, so I'm going to show a little more what I did. By the way, one great thing I like about this, pardon me, is creativity. There may be another way to do it that works better than I did or is acceptable, etc. So don't feel like you're restricted to the way I do it. So let's see if we get to MATLAB. Okay, so there's I did format bank so that even though that was actually maybe not be quite necessary, but remember bank is 2 decimal places. So then I've got the resultant, and I got theta by doing arctan FRX over FRY. And then I just went and did 180 over pi to make it into degrees. So that's going to get my theta. Remember though that arctan is only going to put out an angle between -90 and +90. And it's possible that our angle output is something like 145 degrees or 226 degrees or something like that. So what we need to do is actually do a little bit of conversion work or a little bit of modification work. So let's take a look at one way to approach it. Okay. If the resultant X force is greater than 0, then we're in the -90 to 90 region. And so we can say that the resultant angle is just what's put out. but otherwise we end up needing to add 180. So for example, if I could go to the whiteboard, but well, let me do that really quickly. If we actually had a resultant angle that was over here like this, that should be between 90 and 180, but arctan is going to put it at an angle over here like this. Hopefully you can see what I'm doing. So we need to add 180. So that's what that last line is there. So I wouldn't stress about that too much. Maybe that was a downfall of me doing this exercise. But if you actually do any problems where the resultant is bigger than 180, you have this problem. If and else is something we'll work on later on. I would encourage you not to stress about this too much. Let's make all the examples that we run put out a resultant force in the first or the fourth angle. So it's negative 90 to 90. Okay. So notice that we've got some yellow over here, kind of interesting. And then I have an F print F. So there may be some other ways you can do it, but let's go ahead and run it and see how it works. So I'm going to run it and I'm going to try it with those values there. Okay, so it tells me to add two vectors. Let's see, our F1 was 100 newtons, okay, at a angle of 30 degrees. Okay, and our F2 was 50 newtons. And that was at an angle of 135. See how it turns out. Okay, so it says our resultant, I might have a calculation up here of 99.56 and at an angle of 59.02. So let me just go ahead and move this up a little bit and take a look at the output. Yeah, everything looks good. What I would encourage you to do once you're working with this is maybe run it for a couple easier cases that are more obvious. So remember we had our 3, 4, 5 right triangle. Let's try to do that again. So let's try to run it with a 3, 4, 5 right triangle and see if it'll work. So F1 is going to be 3, okay, and we're going to have it at a magnitude of 0, and F2 at 4 at an angle of 90. And let's see, it says that the resultant angle is 5 at an angle, pardon me, resultant magnitude is 5 at an angle of 53.13. I'm going to try one more. Okay, let's just hang on just a minute. Yeah, let's go ahead and run it. So F1 magnitude, let's imagine that F1 is this way and F2 is down, and let's see if that works. So a magnitude of 40 at an angle of 0, and then F2 magnitude of 30 at negative 90. Let's see how that works. Okay, so the resultant magnitude is 50 and it's an angle below the horizontal. Okay. Well, that's it. Hopefully you will have received from me before you take a look at this is an email noting, hey, this how I'm going to proceed to try to make up for the time lost. I appreciate all of your patience. I'm really sorry about this. There will be a part 2 to this lecture, but I'm probably going to try to record it tomorrow morning. My voice is so much better today than yesterday, and hopefully tomorrow it will be even better. I will try to have an office hour Sunday at some point and be good about checking my email so that we can all get up to speed. One more note, I'm going to make homework number 2 due Monday at 11:59. I understand that it's shorter than a homework number 2 ordinarily would be because shoot, it's Saturday already. But I do want to make it due, and I just want you to do the best you can. I think it's really helpful if we stay on a schedule and we just do the best to keep up with that schedule. Please feel free to contact